Hello and welcome to our lecture on integrals involving exponential and log functions. So we're going to jump right into the rules that we're going to use in this section. So we've got 5 rules here. Some of them we're already familiar with. These rules are for integrals of exponential and log functions. So looking at the first one here, the integral or the antiderivative e to the x is e to the x plus a constant. This one we're already familiar with. The integral of a to the x, so the base is a to the x ln of a plus c. So we can verify that this is the antiderivative by taking the derivative of this side and arriving back at a to the x. This one here we're also familiar with. The integral of 1 over x dx is equal to the natural log of x plus c. Here the absolute value bars are in the rule. You'll see it written this way. Also, you'll see it written with just parentheses around the x. But the understanding is that the domain of the natural log function is all positive real numbers. So you would not have a negative number as an input to the natural log function. So we're familiar with that one. Now, this one here, this antiderivative is arrived at by integrating the natural log of x using the integration by parts method, which is a method we learned in Calculus 2. So we're going to use this rule now, but we're not going to show the derivation because that's beyond the scope of Calculus 1. This rule right here is also derived using the integration by parts technique, like I just said was a Calculus 2 technique that we learned. So we're going to go ahead and use this rule but not show the derivation of it. Now, sometimes you'll see it written like this in a table of rules. Sometimes you'll see it like this, and there are other ways this rule is written in tables, but they are equivalent ways. And so if you were to take the derivative of the right side of any of these rules, you would verify the rule by landing back with the integrand. Okay, so this is the table of rules we're going to work with in section 5.6. So I'm going to start with example 1 here. So I've got the integral of e to the negative x dx. So I have an outer function e to the x with an inner function negative x, basically. So that means I would say that u is equal to negative x. Then du would be negative 1 dx. Now I go back over to my integral and I see what the form looks like. So I've got e to the negative x dx. Right, this here needs to be a positive dx. So I go back over here and I say negative du would have to be positive dx. All right, which makes this part negative du and this part e to the u. All right, so now I've got the integral of e to the u. Let's put the negative out front, du. Okay, so I've got it set up now. So I know my rule says the integral of e to the u is e to the u. So I can say simply that my answer is negative e to the u plus c. Then I go ahead and I replace u with negative x. So I've got negative e to the negative x plus c. And this is my integral. Now looking at the second problem, I'm once again going to say that my power will probably work as my u. Let's try it out. So my power is negative 2x cubed, which means du is negative 6x squared dx. So if I look at my setup, I've got, we'll rearrange it a little. I've got e to the negative 2x cubed times x squared dx. So I don't have this negative 6 there over here, so I need to divide it out of here. So we can say that we have negative 1/6 du, which would make this x squared dx, which I do have. So I can say that x squared dx can be replaced with negative 1/6 du, and this part here is e to the u. So what I do have is the integral of negative 1/6 e to the u du, which according to our rule is negative 1/6 e to the u plus c. Now I go ahead and put u back in, get it in terms of x. I've got e to the negative 2x cubed plus c. So in example 2, we're going to do some more u substitution integration here of the e to the x function. So let's just say our inner function is u is equal to 1 plus e to the x. That would mean du is equal to e to the x dx. Now let's look over here at the form. We've got the square root of 1 plus e to the x, and then we've got e to the x dx. So we have du, and then this root would be square to u. So our integral becomes u to the 1/2 du. So we know that the integral of u to the 1/2 du is u to the 1/2 plus 2/2 divided by 3/2 plus c, which is 2/3 u to the 3/2 plus c. All right, so now I plug back in my function in terms of x, my inner function. So that would be 1 plus e to the x to the 3/2. And then if I want to go ahead and write that with the radical back in, I've got 2/3 square root 1 plus e to the x cubed. All right, let's put the c in here, plus c. So this is our integral, or our antiderivative. All right, let's try another one of these. So this time, it looks like my inner function is 3e to the x minus 2. Du would be 3e to the x dx. So looking at the form of my integral, I've got 3e to the x minus 2 squared times e to the x dx. All right, so I don't have a 3 over here like I do here, so that means I need 1/3 du. I'm dividing by 3 is e to the x dx. So e to the x dx is 1/3 du, and this part here is u squared. So I have the integral of u squared, but the 1/3 in front, du. So if I integrate that, I'll get 1/3 u to the 3 divided by 3 plus c. So that's equal to 1/9 u cubed plus c. Right now I substitute u back in there. U is 3e to the x minus 2, then cubed plus c. Right, so this is my integral of e to the x, 3e to the x minus 2 squared dx. All right, using the u substitution method. Alright, so let's try some more of these. So this time it looks like I have a 2x cubed in the power position for the e to the x function, so I'm going to try setting u equal to 2x cubed. Du would be 6x squared dx. And I'm going to look at the form of my integral. So I've got e to the 2x cubed times 3x squared dx. Okay, so I can see that I have the x squared dx. I have a 3 instead of a 6. And this would be my e to the u. So it looks like I need to divide it in half in order to get that 3. So that would be 3x squared dx. So this part here is 1/2 du. And this part here is e to the u. So I have the integral 1/2 in front, e to the u du. So that's 1/2 e to the u plus c. Substituting back in my u, I have 1/2 e to the 2x cubed plus c. Okay. Okay, one more like this. I've got e to the x to the 4th power, so it makes sense to set u equal to the power x to the 4th. Du would be 4x cubed dx. Looking at the form of my integral, I've got 2x cubed. Let's write the e to the x first, like we've been doing. I've got e to the x to the 4th, 2x cubed dx. Alright, so I don't need a 4, I need a 2. So that's 1/2 du is equal to 2x cubed dx. 2x cubed dx would be 1/2 du. And then e to the x to the 4th would be e to the u. So I've got the integral of e to the u, 1/2 in front, du, 1/2 e to the u plus c, which is equal to 1/2 e to the x to the 4th plus c. Alright, so these aren't too bad using the u substitution method, with the power of the e to the x function generally being a good choice for u. So now we'll move into some definite integrals. So first, we're going to do the u substitution method again, and then we'll deal with the limits of integration. So we've got u equal to 1 minus x, du equal to -1 dx. Alright, now I look over here and I don't have a negative, I just have a positive dx, so I know I'm going to have to say negative du is equal to dx. So the form of my integral so far is e to the u, negative in front, du. Alright, now let's deal with the constants of integration. So when the top number is 2, I want to take that 2, put it in here for x, and solve for u in terms of x. So I get u is equal to 1 minus 2. That's -1. So -1 goes on the upper limit of integration. And then for the lower limit of integration, I've got 1 for x, which goes here. So I have u equals 1 minus 1, which is 0. So the lower limit of integration would be 0 in terms of u. Alright, so now I find the antiderivative, so that's e to the u evaluated between 0 and negative 1. Okay, so now I substitute in. I've got negative e to the negative 1 minus negative e to the 0. So that's equal to negative 1 over e plus e to the 0. That's just 1. Okay, so this is your exact answer right here, which is fine. We don't necessarily need to find a decimal equivalent. You can use your exact answer. All right, so now we got another example here. So we're going to say that u is my power 2x, du is 2dx. Then I look over here and I see that I have dx, but not a 2. So I'm going to divide by 2 and I'll get dx. All right, now let's do the limits of integration while we're at it. So the upper limit of integration now is a 2 in terms of x. So it would be 2 times 2 in terms of u. That would be 4. The lower limit of integration in terms of x is 0. So it would be 2 times 0, which is 0 in terms of u. So putting it all together, I've got the integral between 0 and 4 of e to the u times 1/2 du. All right. So now integrating or finding the antiderivative, I've got e to the u. And this is a definite integral, so we end up with a number evaluated between 0 and 4, 1/2 e to the 4 minus e to the 0. All right, so we know e to the 0 is 1, so this is 1/2 e to the 4 minus 1. So this is a number, so we've evaluated our definite integral. So looking at a, we're going to do some more of these. I've got e to the 1 over x divided by x squared. So we start by saying that u is the power 1 over x. So that's x to the negative 1. So du would be negative x to the negative 2 dx. So that's the same thing as negative 1 over x squared dx. Right, so now I look over here and I see what my integral looks like. So I've got e to the 1 over x times 1 over x squared dx. So I've got the 1 over x squared here and the dx, but not the negative. So I divide by negative. So then I have 1 over x squared dx, which is what I have over here. So that part, this part here is negative du. This part here is e to the u. All right, now let's do the limits of integration. So for the upper limit, I've got 1 over 2. Remember what I'm doing is I'm putting the 2 in for the x. And then the lower limit of integration would be 1 here goes right here. This is 1 over 1, which is 1. All right, so now putting it all together, I have the integral in terms of u is now 1 to 1/2 e to the u negative because of this negative here, then du. All right, so now I'm ready to integrate. I've got negative e to the u evaluated between 1 1/2, which is equal to negative e to the 1/2 minus negative e to the 1, which is negative e to the 1/2 plus e. All right, so that's our result here. For part B, we're going to once again use u substitution, where we're going to say u is the power of the e to the x here, which is 4x to the negative 2. So du is negative 8x to the negative 3 dx. So that's the same thing as saying negative 8 over x to the third dx. Okay, now let's go over here and see how our integral looks. So I've got e to the 4x to the negative 2 times 1 over x cubed dx. So I've got the x cubed and the dx here, but not the negative 8. So I'm going to have to divide by negative 8. So we have negative 1/8 du is equal to 1 over x cubed dx. All right, so now we can say, well, let's go ahead and do the upper and lower limits of integration while we're at it. So the upper limit, starting out with 2 in terms of x, that would go right here. So I've got 4 over 2 squared. That's 4 over 4, so that's 1. And then the lower limit of integration would be 4 over 1 squared. So that's 4. All right, so putting everything into my integral now, I've got the integral between 4 and 1 of e to the u, and then I've got negative 1/8 du. All right, so now I can integrate. I've got negative 1/8 e to the u evaluated between 4 and 1. Okay, so that's equal to negative 1/8 e to the 1 minus e to the 4. All right, so we can just leave it like that. That will be fine. All right, so in this example, we're going to again use u substitution, and it looks like the best approach we could try here would be to attempt this as u right here and see if we can get it to work out. So if u is my inner function and we're saying it's e to the 10x plus 13, du would be 10 e to the 10x, chain rule that is, dx. All right, so if I look at my integral, I have 1 over e to the 10x plus 13 squared times e to the 10x dx. All right, so I have the e to the 10x dx, but not the 10. So I need to divide out the 10. So that makes this part here 1/10 du. This part here 1 over u squared. So I have the integral of, let's call 1 over u squared u to the negative 2 times 1/10 du, put the 1/10 in front, the du here. All right, so if I integrate that, I'll get 1/10 u, raise it up to the negative 1, divide by negative 1 plus c, which is equal to negative 1/10 times 1 over u. All right, so now we put the u back in terms of x. So we get negative 1/10 times 1 over e to the 10x plus 13. All right, so that's there, plus c. Okay, so that's our integral there, and all of that is the integral of e to the 10x, e to the 10x plus 13 squared dx. Okay, so now let's try another one of these. Trying to figure out, using u substitution, what the best choice for u is. So to start out, let's just say that u looks to be this right here, e to the 3x, the inner function. Sine x would be the outer function, of course. So I've got u is e to the 3x. du would be 3e to the 3x using the chain rule dx. All right, so looking at my setup here, I've got sine of e to the 3x times 3e to the 3x dx. So I've got the 3e to the 3x, so this is du, and this is sine of u. So my integral is sine of u du. So we know the antiderivative of the sine would be the negative cosine of u plus c, and that's because the derivative of the cosine is the negative sine times negative would make it positive sine. So subbing back in my u, I have, let's just write it all out, the integral of 3e to the 3x sine of e to the 3x dx is equal to negative cosine of e to the 3x plus c. So now we'll switch gears a little bit and work with the natural logs. So the form I've got here is basically 1 over x type of form. So I'm going to say that my u is x minus 10 and do the u substitution technique again. So du would just be 1 dx. So looking at my integral and how it's set up, I've got 1 over x minus 10 times 3 dx. So I need a 3 in here, so I would multiply to get 3 dx. So that means 3 dx is 3 du, and 1 over x minus 10 is 1 over u. So now my integral becomes the integral of 1 over u, 3 in the front, du. So now I go back and look at my rule table, and I can see that 1 over x dx, if we have 1 over u du, we need this rule here. So the integral would be the natural log of the absolute value of x plus c. So I wrote my rule down here. So we're going to put the bars in here. Like I said, sometimes you don't see the bars in there. They're understood to be there, and you'll just see parentheses. So this means that we have 3 times the natural log of the absolute value of u plus c. Now I go ahead and put my x minus 10 back in. So I've got 3 natural log of x minus 10, the absolute value of it, plus c. And there we go. So looking at example 9, it looks like a rational function, and we're trying to take the integral of that. And what you want to notice, is that if let's just say this is u, and I'm just examining this right now to see if this is going to work. So this would have to be the derivative of this in order for this to be u. So 4x cubed, well, it's a 2, but maybe we would have to divide if this also was divisible by the same number. So this would be 2 times 3, that's 6x, so it is. So this is a good bet for u. So let's just say u is equal to x to the 4th plus 3x squared. And then du would be 4x cubed plus 6x. All right, and this is dx. So then if I look at the form of my integral, I've got 1 over u. This we're saying is u. I'm just going to write it out so we can look at it, see what's going on. Then this top part I'll put over here. All right, and then I'll examine it and I'll see that this is 1 over u. And then this part over here is a multiple of this. So I need to divide by 1/2, basically, to get it to be 2 and 3, which is what we want. All right, so now this part over here is 1/2 du. Okay, so we can set up the integral as putting the 1/2 in front, 1 over u du. All right, so this is going to take the same rule, the ln rule. So there's our rule. So this would be 1/2 natural log of the absolute value of u plus c. All right, now I'm ready to sub u back in. So I've got 1/2 natural log of absolute value of x to the 4th, 3x squared plus c. All right, so I'm just going to leave those bars in there, even though you could see that this is never going to be negative because these are all to even powers. So these could be parentheses as well. But we'll just leave the bars in there. So that's equal to the integral of our original rational looking function here, right? All right, using u substitution and what we know about integrating 1 over x dx, our rule. Okay, so next we're going to take a look at how to integrate a log to any base looking function. All right, so let's go back to the rule table, and we're right here now, log to the base a of x dx, the integral of that. So let's put it in this form here and apply this rule. So here's our rule. So now we can see that a is equal to 2. So we've got the integral of log base 2 of x dx is equal to x divided by the natural log of 2 times the natural log of x minus 1 plus c. All right, so that's all there was to that one, just substituting 2 in for a in the formula. So looking at the setup here, we've got what looks to be a 1 over u setup again. If this is u, let's just try it. U is equal to 1 plus the cosine of x. Du would be negative sine of x dx. And if we look at the way this is set up, we could say we have 1 over 1 plus the cosine of x times the sine of x dx. So that means I need a negative du to be positive sine of x dx. So then this here would be negative du. This here is 1 over u. So I've got the integral of negative 1 over u du. So let's write our rule down again. So there's our rule. So we've got negative natural log of u, absolute value, plus c. All right, subbing back in for u, we've got negative natural log of 1 plus the cosine of x, absolute value, plus c. And that's what the integral of sine of x over 1 plus the cosine of x dx would be. Okay, so this example is a little different. So we might have to try something out here. So if I chose this as my u, you can see this x is going to cause problems here. All right, because I would then have a product. So if I chose ln of 4x as u, then the derivative of the natural log of 4x would be 1 over x. That would get my x in here. So let's attempt u being the natural log of 4x and see where that goes. So if u is the natural log of 4x, du would be 1 over 4x times, using chain rule, times 4 dx. Right, so that's du is equal to, canceling the 4's, 1 over x dx. Right, now let's look at the integral here and see how we can split it up. So what if we took 1 over the natural log of 4x and then put the 9 over x dx together? So then we examine that and we see that this would be 1 over u. 1 over u. This part here. This part here is almost this part here, but we've got this 9 here. So we can say 9 du is 9 over x dx, which would mean this part here is 9 du. Okay, so that will work. So this is equal to 9 times the integral of 1 over u du. Okay, so we can use our same rule that we've been using. So there's our rule. So we have 9 times the natural log of the absolute value of u plus c. Right, now we're ready to put u back in to get our final answer. So that's 9 times the natural log of u. U itself is a natural log. So that goes inside the bars, plus c. Okay, so that's how we would write our answer. So that's equal to the integral, our original integral, and there we have it. So that's the end of the examples that we're going to do to get us familiar with using the table of rules laid out in the first slide. So it gets us started in learning the integrals of exponential and log functions, and then we get into it a little deeper in calculus Calc 2.